Welcome. Today we're diving into a really critical area, safety in chemical plants, specifically looking at potential accidental releases.
That's right. We're focusing on how these potential events are analyzed, how experts try to understand what might happen.
It's about getting a handle on the unexpected, isn't it? From the moment something might escape to all the possible ripple effects.
Exactly. And understanding the science here isn't just for, the engineers on site. It's really for anyone interested in how these complex places manage risks.
How they try to prevent incidents, essentially. We'll be dissecting how experts approach this, starting right at the beginning, the potential release itself.
Think of it like understanding the vulnerabilities. In a chemical plant, a potential release is a key vulnerability.
And what we're discussing, consequence analysis, that's like the plant's way of stress testing those weak points to see what could actually happen.
Precisely. We'll shed some light on that process, starting with how they modeled that initial escape of material.
Okay. And our discussion, it's based on solid ground, right?
Wow.
Scientific principles, standard procedures.
Absolutely. Established science, engineering procedures, and we'll use some illuminating examples from actual consequence analysis work. The focus is really this idea of consequence analysis and the foundational role of source models.
All right, let's unpack that term then. Consequence analysis. Sounds like we're digging into some serious what-ifs. What exactly is it?
Well, simply put, it's the method used to describe what could happen, the effects, if a release incident occurs at a plant.
Okay.
It's about understanding the potential for harm to people, damage to property, if a hazardous material gets out. And that takes into account the material's own hazards.
Like its toxicity, flammability.
Exactly. Toxicity, flammability, potential for explosion, even just the energy it carries. All those inherent properties.
So it's a structured way of thinking through, if this happens, then what? But scientifically based, not just pulling ideas out of thin air.
Definitely not guesswork. There's a strong scientific basis.
So what's the ultimate goal? Why do this deep analysis?
The main goal is really determining the spectrum of possible outcomes from a release. This covers, the more likely scenarios, and also those less likely but potentially very severe ones, the kind we absolutely want to prevent.
Right.
Understanding these potential consequences is just vital. It directly shapes the safety measures put in place.
And I imagine it's crucial for emergency planning, too.
Oh, absolutely fundamental. Knowing the range of what could happen allows for much, much better preparation. You can tailor your response.
That makes total sense. Okay, so how do the experts actually do this consequence analysis? What are the key steps involved?
Well, the process generally involves several key stages. First, you've got to define the release scenario you're looking at.
Like what kind of failure are we considering? A pipe break, operator error.
Exactly. Then you use source models. That's key to describe the initial release itself. How much, how fast, what state it's in.
Okay.
After that, you typically use dispersion models to predict how that release stuff will spread out in the environment.
And finally,
effect models come in. They assess the potential impacts on people, on structures, based on where that material is predicted to go.
source models. That sounds like the absolute starting point.
Yeah.
Figuring out how the material gets out. Tell us more about those. What's their main job?
You got it. Think of source models as the initial description of the release event itself. They're built on fundamental scientific equations.
Physics and chemistry, basically.
Right, representing the physics and chemistry that govern how a material escapes its containment. Their main job is to give a detailed picture of that initial release.
Detail seems really important here. What specific information do these models give us?
A good source model tells you primarily the discharge rate. So how quickly is the material escaping?
Okay, the speed.
Yeah. And also it estimates the total quantity released, or maybe the duration, how long the release lasts. And critically, it describes the physical state of the material as it's released. Is it coming out as a solid, a liquid, a vapor, or maybe some combination?
It's physical state. Yeah, that seems like it'd make a huge difference. A vapor cloud is totally different from a liquid pool.
Totally. The state gas, liquid mixture fundamentally dictates how it behaves next, how it disperses, whether it might ignite its potential impact. So that initial characterization from the source model, it's absolutely foundational for everything that follows in the analysis.
Okay, so we get what source models do. What kinds of release situations do they help analyze? I saw a note about limited aperture releases. What's that?
Yeah. Limited aperture releases, that's just a common category. It describes releases through a specific defined opening.
Like a hole. or a crack in a pipe.
Exactly. A hole, a crack, maybe a valve that's not fully closed. The source models for these help quantify how material flows through those specific openings.
Let's dive into one type then. The notes mention flow of liquid through a hole. What are the key ideas there?
Okay, so this model describes what happens when a liquid escapes through an opening, say in a tank or a pipeline.
Right.
To figure out the rate and amount released, we use fluid mechanics principles, specifically mechanical energy balance equations.
Energy balance.
Yeah.
It sounds like physics class again.
Sort of. Think of it like balancing forces. What's pushing the liquid out that's pressure, the height of the liquid, minus any resistance, like friction as it flows through the hole, that equals the resulting flow rate. These equations factor in pressure, density, liquid height, and friction.
Seems like a careful calculation. Can we maybe look at an example, make it a bit more concrete?
Absolutely. Let's take example 4.1. Imagine a plant operator notices the pressure dropping in a benzene pipeline. Not good.
Definitely not.
They find a small leak, maybe just a 1/4-inch diameter hole. Thankfully, they find it and get it repaired within, say, 90 minutes.
Okay.
Now, let's assume the pressure in that pipe was around 100 psig. Using those principles we just talked about, we can estimate how much benzene actually spilled during that hour and a half.
All right, walk us through it simply. How do we get from that tiny hole and pressure to actual gallons spilled?
Okay. First, you calculate the area of that leak. A 1/4-inch hole. It's a really small area when you think in square feet.
Tiny.
Then there's an equation. It uses the pressure pushing the benzene out, the density of benzene, which is about 54.9 pounds per cubic foot,
Okay.
and something called a discharge coefficient. Think of that as like a reality check factor. Real holes aren't perfectly smooth, right?
They're jagged or irregular.
So the actual flow is usually a bit less than some perfect theoretical model predicts. This coefficient accounts for that. We combine those things.
That gives you.
That lets us calculate the mass flow rate. So how many pounds of benzene are escaping every single second?
Okay, so even if the hole's small, that constant pressure is pushing stuff out continuously. What's the maybe surprising result here?
Well, after you crunch the numbers, and you have to be careful with units, of course, it turns out that even with that small leak, over 90 minutes, something like 700, 990 pounds of benzene spilled.
Wow. How much is that in gallons?
That's roughly 10 to find in 90 gallons.
Over 1,000 gallons.
Yeah.
From a 1/4-inch hole repaired in 90 minutes.
Yeah. It really drives home a key safety lesson, doesn't it? Even seemingly minor leaks, if they go on for a bit, can lead to significant releases. Shows why early detection and quick repairs are so critical.
Absolutely. That really puts it in perspective. Okay, what if the leak isn't in a pipe, but in, say, a big storage tank? Does the model change much?
It does adapt, yes. The model for flow of liquid through a hole in a tank specifically brings in the height of the liquid level above the leak point.
Because that adds extra pressure, right? The weight of the liquid.
Exactly. The higher the liquid column, the greater the pressure down at the leak, and so the faster the discharge rate, initially anyway. The equations are similar, but they explicitly include that liquid height contribution to the pressure, along with the liquid density.
Can we get another example? Maybe a tank leak scenario?
Sure. Let's look at example 4.2. Picture a cylindrical tank. It's holding benzene, but there's pressurized nitrogen gas above the liquid that's pretty common to maintain pressure or prevent air getting in.
Okay.
Now imagine this tank develops a puncture, maybe a 1-inch diameter hole, about 5 feet up from the ground. We'd know the tank dimensions, the nitrogen pressure, the starting benzene level, and its density.
Right.
The question is, how much benzene spills out, and how long does it take for the leak to essentially stop or slow right down?
Sounds like it could be a bigger problem than the pipeline, Nick.
It certainly can be. The calculation involves the leak area 1-inch hole this time, a discharge coefficient, often around 0.61 for a sharp-edged hole like a puncture. And importantly, it has to account for the liquid level dropping as the benzene leaks out.
Oh, right. Because as the level drops, the pressure at the hole decreases.
Exactly. So the discharge rate isn't constant, it slows down over time. The analysis for this example shows something like 4,506 gallons could spill over about 56 minutes.
Almost 4,600 gallons in under an hour. That's quite sobering.
It is. It really underscores the potential scale of releases from storage vessels and why things like secondary containment like dikes or bunds around tanks and rapid emergency response plans are so critical.
Definitely. Okay, we've talked about leaks through holes. What about when a pipe doesn't just leak, but actually ruptures or breaks completely? How do you model that for liquids?
Right, the flow of liquids through pipes model gets a bit more intricate. The main reason is friction.
Friction along the length of the pipe.
Exactly. As the liquid travels along the pipe, there's resistance to flow. So you need to account for the pipe's dimensions, diameter, length, how rough the inside surface is, any fittings like elbows or valves because they add extra resistance, and of course the overall pressure difference that's driving the flow in the first place.
So it's not just about the size of the break at the end. The whole journey through the pipe matters.
Precisely. We use equations that incorporate a friction factor. There are different ways to estimate this, like using the Fanning friction factor or the Colebrook equation. These help quantify the energy loss due to friction.
Okay.
We also consider what's called excess head loss. That's the extra resistance from those bends and fittings. And the Reynolds number is important too. It helps figure out if the flow is smooth, laminar, or turbulent.
Can you give us a practical example for flow through a ruptured pipe?
Let's take example 4.3. Imagine a big tank holding contaminated water, maybe some hazardous waste mixed in. A pipe connected to it ruptures. Let's say it's a steel pipe, 100 millimeters inside diameter, 33 meters long. The water starts draining out just due to the height difference between the tank level and the break.
Okay.
We'd know the water's density and viscosity and that height difference. The goal is to calculate the flow rate. How fast is this contaminated water escaping?
Sounds like a few more moving parts in that calculation.
It is. The solution often needs an iterative approach. You see, the Reynolds number, which you need to find the friction factor, actually depends on the flow velocity.
Which is what you're trying to find.
Exactly. So you might have to make an initial guess for velocity, calculate Reynolds number, find the friction factor, recalculate velocity, and repeat until it converges.
Bit of a circular process then.
It can be, but working through it, for this example, you might find the flow rate is about, say, 3.76 meters per second, which translates to about 28.8 kilograms per second.
Okay.
It really shows how the pipe system characteristics, length, diameter, roughness, significantly control the release rate in a rupture scenario.
All right, we've covered liquids quite a bit, holes, tanks, pipes. What about gases or vapors? They must behave quite differently when they escape.
Oh, absolutely. The physics changes quite a bit. The flow of vapor through holes model introduces some pretty unique concepts. One of them, most critical, is something called choked flow.
Choked flow, what does that mean?
It happens when the pressure downstream outside the hole is significantly lower than the pressure upstream inside the container. As that pressure difference gets bigger, the gas escaping through the hole speeds up faster and faster until it reaches the speed of sound for that specific gas under those specific conditions of temperature and pressure.
The speed of sound. Wow, that's incredibly fast.
It really is. And here's the fascinating part. Once the flow hits that sonic velocity, we say it's choked.
Okay.
And once it's choked, the mass flow rate, the amount of gas escaping per second, cannot increase any further. Even if you drop the downstream pressure even lower, like creating a near vacuum outside.
Wait, really? So lowering the outside pressure more doesn't make more gas come out faster once it hits that limit?
Correct. It's counterintuitive, isn't it?
Yeah.
The flow rate becomes independent of the downstream pressure. It's entirely dictated by the upstream conditions, the pressure, the temperature, and the properties of the gas itself.
That's wild. So there's like a physical speed limit for gas escaping a hole.
Essentially, yes. The concept of choked pressure is related to this. It's the critical downstream pressure relative to the upstream pressure at or below which this choking phenomenon occurs.
And how do you figure that out?
It depends on the upstream pressure and a property of the gas called the heat capacity ratio, often represented by the Greek letter gamma. It basically relates to how the gas's internal energy changes with temperature.
Okay, this definitely needs an example.
Let's do example 4.4. Imagine a tank holding nitrogen gas at, say, 200 psi pressure and 80 degrees Fahrenheit. A small hole forms, maybe 0.1 inches in diameter. We want to know the mass flow rate of nitrogen leaking out. We'd also need the heat capacity ratio for nitrogen, which is about 1.41.
Right, so how's the calculation work?
Well, first you'd calculate that choked pressure using the 200 psig and the gamma value. Then you figure out the area of that tiny 0.1-inch hole. Finally, you plug these values, upstream pressure, temperature, gas properties like molecular weight and gamma, and the area into a specific equation for choked flow. For this nitrogen example, the result comes out to about 3.86 pounds per second.
3.86 pounds per second through a 0.1-inch hole.
Okay.
That still sounds like quite a bit of gas escaping quickly.
It is. It demonstrates how we quantify vapor release rates, and it really highlights this interesting choked flow phenomenon.
So even for gases, we can predict escape rates, and there's this sort of natural speed limit. What about gases escaping through pipes, not just holes? Is that even more complex than liquids in pipes?
It definitely can be, yes. Modeling gas flow through pipes adds the major factor of compressibility.
Because gases compress and expand easily with pressure changes, unlike liquids.
Precisely. As the gas flows down the pipe and the pressure drops, its volume changes, its density changes. That significantly complicates the fluid dynamics compared to liquids, which are mostly incompressible.
Okay, what else?
We also often need to consider if the flow is happening so fast that there's not much time for heat to transfer in or out, that's called adiabatic flow, or if it's slower, allowing the gas temperature to stay relatively constant, that's isothermal flow. The math is different for each.
Right.
And just like with holes, we can run into sonic velocity issues in pipes, especially at the exit or if there's a restriction. The Mach number, the ratio of the flow speed to the local speed of sound, becomes important.
Mach number, like with fighter jets.
Exactly the same concept. If the Mach number reaches 1 inside the pipe or at the exit, the flow is sonic, and again, you can get choked flow conditions, limiting the maximum possible release rate.
Okay, example time for this one too, please. This sounds tricky.
Let's try example 4.5. Picture a storage vessel with liquid ethylene oxide. Above the liquid, there's vapor at, say, 81 PC and 80 degrees Fahrenheit. This vapor needs to be vented, perhaps through a pressure relief system. The vent system involves a long, relatively narrow pipe, maybe 250 feet long, with a 1-inch internal diameter. And it's just discharging straight to the atmosphere, which is at about 14.7 psi. The question is, what's the mass flow rate of this ethylene oxide vapor through the pipe?
Okay, long pipe, compressible gas, significant pressure drop.
Yeah, sounds complicated.
It is. You've got compressible flow, you've got the potential for choking somewhere along that pipe or right at the exit, and you have to account for friction losses over that whole 250-foot length.
So how do you solve that?
It often requires, again, iterative calculations or using specialized equations designed for, say, adiabatic flow with friction or isothermal flow with friction. There are established formulas for these cases. Working through them, you'd arrive at an estimated mass flow rate. For this example, it might be something like 4.16 pounds per second.
Still a significant rate. It really highlights how many factors play into gas releases through pipes.
It does. The interplay between pressure drop, compressibility, friction, and potential choking makes it one of the more complex source modeling scenarios. Okay, we've talked liquids, we've talked gases. Yeah. But what about when a liquid changes state as it's released? I think the notes mentioned flashing liquids. What's that about?
Yes, flashing liquids. This happens when you have a liquid stored under pressure, but at a temperature that's above its normal boiling point at atmospheric pressure.
Like water in a pressure cooker.
Exactly like that. Or think of LPG, liquefied petroleum gas, stored under pressure as a liquid, but it would normally be a gas at room temperature and pressure.
So what happens when it's released?
When the pressure is suddenly released, like through a leak or rupture, the liquid finds itself instantly superheated relative to the new lower pressure environment.
Superheated, meaning it wants to boil, like right now.
Precisely. And so a portion of it does boil very rapidly and almost instantaneously. It flashes into vapor.
Okay, so you get a mixture coming out.
Yes. You end up with a two-phase flow, a mixture of the remaining liquid, now cooled down by the evaporation, and the newly formed vapor. This flashing can be quite vigorous, sometimes creating fine mists or aerosols, and it definitely affects how the material disperses.
Sounds like modeling that would be extra challenging. How do the source models handle flashing?
The models specifically for flashing liquids aim to do two main things. Calculate the fraction of the liquid that vaporizes upon release, and calculate the overall mass flow rate of the resulting two-phase mixture. These models often rely heavily on the thermodynamic properties of the substance.
About dynamics.
Yeah.
Like enthalpy, heat of vaporization.
Exactly those. The enthalpy of vaporization, how much energy it takes to boil, and the specific heat capacity, how much energy it takes to change temperature, are key inputs.
Let's see an example of this flashing phenomenon.
Okay, consider example 4-6, a simple one. Imagine you have just 1 pound of saturated liquid water, but it's held in a vessel at 350 degrees Fahrenheit. That's way above the normal boiling point of 212 degrees Fahrenheit.
Right, because it must be under pressure.
Exactly. Now, if that vessel ruptures and the pressure instantly drops to atmospheric pressure, we want to know what percentage of that water immediately flashes into steam.
How do you figure that out?
You use thermodynamic data like from steam tables looking at the energy content, enthalpy, of the liquid at 350 degrees AFI and the energy content of liquid and vapor at atmospheric pressure boiling point. The difference in energy combined with the heat of vaporization tells you how much can flash.
Found a result.
The calculation shows that about 14.59%, or roughly 0.146 pounds of that original pound of water, will instantly vaporize.
So not all of it, but a significant chunk turns to steam right away.
Yes, and that immediate vapor generation dramatically changes the nature of the release compared to just spilling liquid water at, say, room temperature.
Makes sense. Can we see an example with a chemical more typical in industry?
Sure, let's look at example 4.7 using liquid ammonia this time. Imagine ammonia stored as a liquid at 24 degrees C in a tank. A pipe connected to it breaks off near the tank. Say the pipe has a diameter of about 0.0945 meters.
Okay. Ammonia boils well below 24 degrees C at atmospheric pressure, right?
Right. Its normal boiling point is way down at -33 degrees. So at 24 degrees C, it's definitely a flashing liquid if released to atmospheric pressure.
So what happens when that pipe breaks?
We'd know the vapor pressure of ammonia at 24 degrees, which is significantly above atmospheric, the atmospheric pressure outside, a discharge coefficient for the break, and the liquid ammonia density. We want to calculate the mass flow rate.
Is there a special equation for this?
Yes, there are specific equations developed for modeling flashing liquid flow through orifices or short pipes. They account for that pressure difference and the fluid properties. Plugging in the numbers for this ammonia scenario, you get a calculated mass flow rate of about 97.6 kilograms per second.
Wow. Nearly 100 kilos per second.
Yeah, it's potentially a very, very high release rate. That rapid vaporization effectively helps push the material out very quickly. It really highlights why releases of flashing liquids can be particularly hazardous.
Absolutely. That's a massive amount escaping almost instantly. Okay, we've covered a really wide range of release types and the source models used. But I remember seeing a distinction mentioned between worst case and realistic release analysis. What's the difference there, and why look at both?
That's a really crucial distinction in safety analysis. Let's start with worst case.
Yep.
Worst case incident analysis involves looking at, well, pretty much the worst thing that could conceivably happen. You assume a catastrophic failure.
Like a huge tank just instantly splitting open.
Exactly. A sudden, complete rupture of the largest vessel containing the hazardous material, leading to an almost instantaneous release of its entire inventory.
Yikes.
And on top of that, you typically assume very specific unfavorable weather conditions, usually what's called F stability, very stable air, meaning anything released doesn't mix or disperse well, combined with very low wind speed, like 1.5 meters per second.
So maximizing the potential concentration and footprint of the release.
Precisely. The whole point of a worst-case analysis isn't necessarily to predict something likely to happen, it's to model the absolute maximum potential impact.
Why do that then, if it's so unlikely?
It's often a regulatory requirement. For instance, the EPA's Risk Management Plan, RMP rule in the US, requires facilities to analyze these worst-case scenarios. It helps define the largest possible zone that could be affected under the most adverse conditions, which informs emergency planning boundaries and community awareness.
Okay, so that's worst case. Maximum impact, regulatory driven. How does realistic analysis differ?
Realistic release scenarios, sometimes called alternative scenarios, try to represent failures that are more probable based on historical incident data, equipment reliability studies, things like that.
So not the instantaneous failure of the biggest tank, but maybe.
Maybe a more typical equipment failure, like a rupture in a specific size of pipe, perhaps related to its diameter rather than the whole vessel going at once. Or a leak from a pump seal or a relief valve sticking open, things that happen more often.
And the goal of analyzing those.
This is more for the facility's own internal risk assessment and safety management. Analyzing these more probable, realistic incidents helps them understand the likely consequences of failures they might actually face.
Right, so they can prioritize.
Exactly. It helps prioritize safety improvements, tailor operator training, refine specific emergency procedures to address the risks that are statistically more likely to occur within their plant.
So worst case sets the outer boundary, maybe for regulators and community planning, while realistic helps the plant focus its day-to-day safety efforts.
That's a great way to put it. Both types of analysis give you vital but different pieces of the safety puzzle. You really need both for a comprehensive understanding, the extreme possibilities and the more probable ones.
This has been incredibly insightful, really peeling back the layers on how potential releases are understood in chemical plants If we were to summarize, what are the absolute key takeaways about consequence analysis and these source models?
I think the biggest takeaway is just how essential consequence analysis is, and that it all starts with those source models we've discussed. They're the foundation.
Right, defining that initial release, how fast, how much, what state.
Exactly. That information is the absolute bedrock. Without a good source term from the model, you can't accurately predict how the material will disperse or what harm it might cause later on.
And it's clearly not a simple single calculation. You need to consider all sorts of scenarios.
Absolutely. A thorough safety assessment looks at a whole spectrum from those smaller, maybe more frequent leaks or pipe breaks.
The realistic ones.
Right, all the way up to those hypothetical but potentially devastating worst-case failures. You need that full picture for robust safety planning and effective emergency preparedness.
It really gives you an appreciation, doesn't it, for the science and the rigor that goes into these often unseen safety protocols, not just in chemical plants, but anywhere hazardous materials are handled.
It really does. And for anyone listening who finds this interesting, what we've covered today with source models is really just the first piece.
There's more to the puzzle.
Oh, yeah. The next steps involve dispersion modeling, figuring out where that released cloud or pool actually goes in the environment, how it spreads and dilutes. And then there's effect modeling, looking at the impacts of toxicity, or modeling potential fires or explosions if the material is flammable.
So plenty more layers to explore for a full understanding.
Definitely. Exploring those areas gives you an even deeper insight into the complete consequence analysis process and ultimately how facilities work constantly to prevent incidents and protect people.
Well, thank you for walking us through this complex but crucial topic. It's certainly given me, and hopefully you listening, a much clearer picture of the science behind industrial safety. Until next time, keep asking questions.